All right, so we're going to do the entire curve sketching algorithm for this function over here. Let's start with the x and y intercept. For the x-intercept, it's just the solution to the top. The bottom's going to multiply with 0. So the solution is just going to be positive 1 for the x-intercept. For the y-intercept, going to sub in x as 0 and solve. So 0 minus 1 is negative 1. E to the power of 0 is 1. So negative 1 divided by 1 is just negative 1. You can do that in your calculator as well. Just sub in x as 0. You'll get your y-intercept. For the vertical asymptote, we have an e function in the bottom. And e functions can never be solved if they're simple e functions because an e function will never hit 0. So there's definitely no vertical asymptote. For the horizontal asymptote, the rules are not usual because we generally have a regular function, a polynomial function on the top, a polynomial function on the bottom, and we use the degrees to find out whether it's horizontal or oblique. But what happens when you have a linear function over an e function? Well, a linear function we know is just a straight line like that, and an e function is like this. So when we divide these two functions by each other, the left side is not really going to have much of an asymptote because the e value is really small. But on the right side, the e value is extremely large, which means when you divide this by this side, there will be an asymptote and it will approach 0. That being said, this is a bit hard to figure out, so maybe you want to leave this blank, but I know that we're going to have a horizontal asymptote at y equals to 0, but it's only going to apply towards the right side. You really don't need to know this because you can use your n behaviors later on to figure out the exact same thing in the sketch. You don't need the horizontal asymptote, so I'll do this question without even using the horizontal asymptote. Now let's derive this function to find our critical points. We're using quotient rule here, so let's do our quotient rule. And I can simplify this. I'll combine these two like terms. And now I can take away an e to the x from all three of them because they all have 1. So I'm just left with 2 minus x over e to the x. This is my derived function. Now to find my critical points, I just want to make this equal to 0 and solve. So the denominator is just going to disappear. And my critical point is just going to be x equals to 2. I'll put this on a number line to figure out whether it's a maximum or minimum. So I'll start by picking a value slightly less than 2. I'll pick 0. I'll sub it in the derived equation. 2 minus 0 divided by e to the 0, that's just positive 2. Positive 2 means if you get a positive number, it means the function is increasing. Pick a value slightly higher, I'll pick 3. So 2 minus 3 is negative 1. Negative 1 over e to the power of 3, that's just a negative value. So I know that it's decreasing after here, which means that this is a maximum. So I know I have a max. The x value is 2. To find the y value, I'll sub in 2 back into my original equations. 2 minus 1 divided by e to the power of 2 is just 0.14. That's rounded to 2 decimal places. The next thing we want to do is just state our intervals of increase and decrease from our number line. So we know that the increase is from negative infinity to 2. And for decrease, it's from 2 till positive infinity. Now we can do the second derivation to find our inflection points. So I'm going to just derive this function again. I'll do it over here. Again, it's quotient rule. F double prime x equals F prime g minus g prime F over g squared, very similar to the first one. I will simplify the top. I'll combine like terms in the top. And I'll cancel out an e from all three of these again, because it's possible. So my second derivation is just negative 3 plus x over e to the x. I'll make this equal to 0 and solve again to find the inflection point. My inflection point is just x equals 3. I'll put this on a number line again to find my intervals of concave up and concave down. So I'll pick a value less than 3. I'll pick 0 again, and I'll sub it into my derived equation here. So negative 3 plus 0 is negative 3 divided by 1. So it's negative 3. So if it's negative, it's going to be concave down. And if I pick a value after this, I'll pick 4. That's going to be positive 1 over e, which is positive. So if it's positive, it's concave up. Then finally, I'll put this point back into my original equation to find what my inflection point is. So it's 3 comma 0.099. So basically 0.1. If you round it, it's really close to 0.1. It's just slightly lower than this point here. So now I can sketch this out. So on my sketch, I'm going to start with all my points. Remember, I'm going to ignore the horizontal asymptote for now, and I'll just mark it at the end. But I know that my x-intercept is positive 1 and my y-intercept is negative 1. I know that my maximum is 2 and 0.14. 2 and 0.14 should be somewhere here. And then I know that my inflection point is 3 and 0.1. 3 and 0.1. So looks something like this, the 4 points. Okay, so if we connect these, we know that till positive 3 till here, this is all concave down. So we know this all connects like this. And we know it still continues as concave down. So it's going to keep going like this, basically. And now over here, we know it switches to concave up. Okay, but how would you know where, if you didn't know that the horizontal asymptote was at y equals to 0, how would you know how to draw this? Well, just pick any high number like 10 or 15 and sub it into the equation and put it in your calculator. If I put 10 or 15 or 20 in this, I would get 0 point something very close to 0. That way you'd be able to tell this end behavior has a horizontal asymptote at y equals to 0. And when this becomes concave up, it just hugs this asymptote the rest of the time. That's how the graph is going to look like. You can label the points now. Negative 1, 1, 2 and 0.14 and 3 and 0.1. And that's how you sketch this function.